Good morning, everyone. In previous class, we have discussed about application of joint light distortion, right? Today we will start the new topic of coordination chemistry, that is color and electronic spectra. So first we discuss about the color of coordination complexes, then we will discuss about the electronic spectrum of the coordination complexes. Okay. Now, color of any system is because of absorption of UV light or of visible light and also reflection of visual light. Okay. In case of coordination complexes, color arises because of excitation of electron from low energy orbital or low energy level to high energy level by absorption of UV visual light, basically visual light. Okay. So why color? Color of any compound is due to color of any compound or complex is due to electronic transition due to electronic transition via absorption of visible light. Visible light is must because our eyes are not able to see IR radiation, UV radiation, microwave radiation, radio wave radiation, right? So it is necessary for any system to show absorption in visible region. For example, if any system absorbs UV light, then it will also most probably emit UV light or reflect some part of UV light. Then, as our eyes are not able to see or not suitable to see the UV light, therefore there will be no color. So any system will show color only when there is interaction of that particular compound with the absorption of visible light. For example, if we have a complex CiH2O6 3 plus and it has D1 configuration. This is D1 configuration complex, D1 octahedral system. And there is one electron. This is T2G set. This is EG set, right? And this complex absorb light, absorption of light, right? On absorption of light, there will be excitation of electron from T2G set to EG set like this. This is T2G set, this is EG set, right? If the energy of this set is E1 and energy of EG set is E2, then delta E, that is the energy difference between these two energy levels, is equal to E2 minus E1, or delta E you can say is equal to Hc by lambda, right? Well, lambda is the wavelength that has been absorbed by the particular complex. So if the energy difference is this energy difference between E and T2 is different, it means the complex will absorb different kind of light, means different kind of complexes, because different kind of complexes has different kind of energy difference between T2G and AG set. The different in the, you can say the energy difference between two energy level is different for different kind of complexes. Therefore, the complexes will absorb, yeah, different kind of complexes will absorb different kind of wavelength. Therefore, they have different kind of interaction or different kind of absorption of UV light, resulting into showing different kind of color. It means the color of complexes depends upon the energy difference between energy levels. If energy level between two complexes are same, then they will mostly show same kind of color. If the energy difference between two or more complexes are different, then they will have different colors. Okay. And when any complex absorb or interact with UV light, then it is the reflected light that is seen by our eyes. For example, if we have a substrate or a complex when white light interact with this particular complex or complex interact with white light that includes seven color that is called pure. Let us assume this complex absorb yellow light, right? Yellow light has been absorbed by this complex. This is absorbed light, right? Then if this complex absorb yellow light, then it will reflect the violet light. And this is the violet light that is seen by our eyes, right? It means when any complex absorb yellow light, the color of complex will be violet, not yellow, right? Means absorbed light and reflected light. The light that has been, that is, we can say the light that is reflected by complex or reflected by any substance is seen by our eyes, and that light will be the color of that particular complex or that particular substance. Okay, these two lights, absorb light and reflected light, are complementary to each other. These are called complementary light. These are also called complementary color or complementary light. Complementary light. There is an artist color wheel suggesting the complementary light of different kind of colors. For example, if we have, it is like PBGYOR. This is artist color wheel. From this wheel, we will be able to find complementary color of different colors, complementary light of different kind of lights. Actually, there are more number of variation in color, but these are the common or these are the main colors that has been shown in this artist color wheel. So the violet, the complementary color of violet light is yellow. Means if any system absorb violet light, then it will show yellow color. Similarly, if any system absorb yellow color, it will show yellow light, it will show violet color. Similarly, complementary of blue is orange, complementary of red is green. Means if any system absorbs red light, then it will show green color. If any complex absorbs a green light, then it will show red color. If any complex absorbs orange light, then it will show blue color. Similarly, if any complex absorbs blue light, it will show orange color. So this is all about the complementary, yeah, important complementary color that can be shown, that can be represented by the artist color wheel, right? So this is all about the reason behind the color of complexes. The color of complex is because of electronic transition from low energy to high energy level by absorption of visible light, because our eyes are able to see only visible light, right? The energy difference between different kind of complexes leads to absorption of different kind of light by different complexes, resulting into different kind of reflected light that leads to different kind of color of different complexes. It is the complementary light that is reflected by complex, means the light absorbed by the complexes and light reflected by the complexes are complementary to each other, and the complementary light can be shown by the artist color wheel, where the complementary color of yellow is the violet, complementary color of orange the blue, complementary color of red is the green, right? It means if any system or any complex absorbs blue light, then the color or light reflected by the complex will be orange, and that will be the color of that particular complex. Okay. Now we will move to the electronic transition. As we have discussed that the color arises because of absorption of visible light. Absorption occurs because of excitation of electron from low energy level to high energy level. This is the low energy level, low energy level. This is the high energy level, right? Yeah, we can say this is the E1, this is the E2, and when electron moves from this energy level to this energy level, there is absorption of light. For example, here we are considering visible light, right? Okay. But there are some restrictions. What kind of restrictions? Whether this particular electron on absorption of light will excite to this energy level or not. There are some restrictions. All kind of light, or we can say all kind of conditions do not always leads to excitation of electron from this low energy level to high energy level. Means when the sorry, when there is excitation of electron from low energy level to high energy level, there is some rule that governs whether excitation of electron from low energy level to high energy level will occur or not. So these rules are called selection rule, because if there is, although you put, although there are many cases where there are white light and many electrons are present in low energy level, but no electrons undergo excitation from low energy level to high energy level. It means there are some restrictions, there are some conditions that decide whether any electron that lies in low energy level will excite to high energy level, or it will not go to it will not travel from low energy level to high energy level. These restrictions are called selection rules, right? Then it means we first try to learn what are the selection rule, what are the conditions that decide whether any electron on absorption of light will move from low energy level to high energy level. Okay, after that we will be able to predict which kind of light the particular complex absorbs. On the basis of that, we will be able to predict the color of a particular complex. Okay, so here we are going to discuss the selection rules. Selection rules for electronic transition. Selection rules for electronic transition. Right? Selection rule decide, or selection rule predict whether in any complex there will be electronic transition, or a particular complex will show electronic transition or not. Okay, so there are mainly there are two type of selection rule, or there are two selection rules. There are two selection rules for electronic transition in coordination complexes. There are two selection rule for electronic transition in coordination complexes. Okay. First is the Laporte selection rule, and second one is the spin selection rule. If any complex follow both these selection rules, then it means there is very high probability of excitation of electron from low energy level to high energy level. If there is more probability of excitation of electron from low energy level to high energy level, it means there is more probability of absorption of visible light by that particular kind of complex, by that particular complex, right? Means absorption of light by any complex, because absorption of light leads to electronic transition. If there is possibility of electronic transition, there will be absorption of light. Means if any complex follow the selection rules, then there is possibility of electronic transition only in such condition there will be absorption of light. If any complex do not follow any of the selection rule, then there will be no possibility of excitation of electron from low energy to high energy level. It means there will be no absorption of light that particular complex. If complex do not absorb light, then it will also not reflect the light. Then there will be no color for that particular complex. Okay. So color is because of absorption of light. Whether any complex will absorb light or not will depend upon the selection rule. There are two selection rules, that is Laporte selection rule, spin selection rule. If both the complexes follow these rules, then there is absorption of light. If they do not follow the selection rule, there will be no absorption of light. If there will be absorption of light, then there may be possibility of showing color. Uh, but if complex do not observe visible light, there is no excitation of electron, then there will be no color for that particular complex. So this is this Laporte selection rule. This is the spin selection rule. So for any system to show color, there must be excitation of electron. There must be electronic transition. For a system to show electronic transition, it must follow, yeah, it should follow the selection rule corresponding to the electronic transition. There are two rules: spin selection rule and Laporte selection rule. Right? So why selection rule? Why the criteria that is given by selection rule is necessary? Yeah, we can say that is uh, mandatory to follow by complex, because if complexes do not obey the selection rule, do not follow the selection rule, then there will be no electronic transition. If there will be no electronic transition, there will be no absorption of light, no absorption of light, no reflection of light, there will be no color of the complex. Okay. So Laporte selection rule and spin selection rule. First, we will try to learn about what is the Laporte selection rule. After that, we will try to learn about or try to get some knowledge about spin selection rule. Both these rules are very simple. First, we will discuss about Laporte selection rule. Right? Laporte selection rule suggests that when there is electronic transition between two states, right? This is only E1 energy level to E2. When there is electronic transition between two energy levels, the delta L should be plus minus 1. The difference between the difference between L values of E2 and E1 states should be either plus 1 or minus 1. Right? For example, if we have DD transition. So what is this? For electronic transition, here we are, yeah, we can say during electronic transition, the statement of Laporte selection rule is that during electronic transition, delta L should be plus minus 1. This is the Laporte selection rule. If we have a electronic transition from T2G set to EG set, right? This is T2G set to EG set. T2G set is a d orbital, EG set also d orbital. T2G set is made up of d orbital, EG set is made up of d orbitals. L value for d orbital is 2. Similarly, L value for d orbital is 2. Means electronic transition between two states, the difference between these two states will be 2 minus 2, that is 0. Means when there is DD transition between two energy states, means when there is electronic transition between two D energy levels, then difference in the value of L is 0. Means this transition, this DD transition is not obeying Laporte selection rule. Means DD transition is Laporte forbidden. We can say DD transition is Laporte forbidden. Means when there is DD transition in complexes, then this transition is Laporte forbidden, because it do not obey. Yeah, we can say that it doesn't obey the Laporte selection rule because of same L values for both energy levels, right? So according to Laporte selection rule, we can say the DD transition is Laporte forbidden. Okay. Now here we are considering the another complex. For example, if we have a complex like MnO4 minus, right? In MnO4 minus, there is excitation of there is transfer of electron, excitation of electron from the 2p in a 2p orbital of the oxygen to the backend 3d orbital of the manganese, because manganese in +7 oxidation state, it had D0 configuration, means it has backend 3d orbital. Oxygen minus, oxygen 2 minus has 2h2 2p6 is a filled orbital, means 2p. So in case of MnO4 minus, excitation of electron occur from 2p or 2p band or energy level of oxygen to the 3d energy level of manganese. The electronic transition between two state 2p to 3d. Here for p, L value is equal to 1. Here for d, L value is equal to 2. The difference between these two energy states is delta L 2 minus 1. That is what? Plus 1. It means this kind of transition, that P to D transition, is Laporte allowed. So this kind of transition is Laporte allowed. Means PD transition, the electronic transition from orbital, that is basically uh, basically p orbital to a orbital that is basically a d orbital, is Laporte allowed. Means in this condition, there will be very high possibility of electronic transition. There will be more excitation of electron from low energy level to high energy level. There will be more possibility of absorption of light as compared to this particular complex, right? The complexes which are Laporte allowed means they have more tendency of excitation of electron from low energy to high energy level. It means they have more absorption of light. More absorption means more number of photons are absorbed by the particular complex. That particular complex, more number of uh, more the number of photons are absorbed by the complex, a more number of light absorbed by the complex, more will be the reflected light also. It means the color of the particular complex will be more intense, because more the intensity of reflected light, more the intensity of reflected light means more intense will be the color. Right? So here, in case of Laporte selection rule, the PD transition is allowed. Similarly, if we consider about transition from S to P, right? L value 0, yeah, transition between two energy states. One is the basically state having nature of S, and another state which is basically of nature having P. Then this kind of transition will be, here the delta L will be plus 1, right? This will be plus 1. It means this is Laporte allowed. Similarly, P to P, no, it is Laporte forbidden. S to D, no, it is Laporte forbidden, because difference delta L is plus 2y, L equal to 0, L equal to 2, right? Similarly, P to D, yes, allowed. T to F, yes, allowed. Laporte allowed. And P to F, no, this is Laporte forbidden, because for P, L equal to 1, for F, L equal to 3, then L, the delta L will be 3 minus 1, that is plus 2. So it is Laporte forbidden. So by considering the L values of different kind of state, we will be able to predict whether a given transition is Laporte forbidden or Laporte allowed. If any complex obey the Laporte selection rule, because electronic transition between two states leads to the difference in delta value, difference in L value either plus 1 or minus 1. It means that particular complex will absorb, yeah, that particular complex will have more possibility of electronic transition, hence more absorption of light, hence more also reflection of light, hence more the intensity of color. We can here write it. If Laporte rule is allowed, means more possibility of electronic transition, more possibility of electronic transition, or more favorability of electronic transition, a more tendency of electronic transition. This leads to more the possibility of electronic transition, more will be the absorption of light, more will be the absorption of light. In most of the cases, this will also leads to more will be reflected light. This leads to more the intensity of color. Intensity means darkness, more the intensity of color. If Laporte rule is forbidden, lesser the possibility of electronic transition, lesser will be the amount of reflected light, lesser will be the intensity of color. That means weak color, light color. Similarly, we can say if Laporte rule is forbidden, Laporte rule is forbidden means lesser possibility of electronic transition, lesser possibility of electronic transition, lesser the absorption of light, lesser the absorption of light, lesser will be a quantity or amount of reflected light, lesser the amount of reflected light, and weak color, weak color, or we can say lesser the intensity of color. In some cases, that can be colorless, but it is also based on the spin selection rule, right? Lesser the intensity of color. Okay, so this is all about the Laporte selection rule. It is very easy to predict whether a given complex will obey a Laporte selection rule or not. If any system is obeying Laporte selection rule, means there will be more possibility of electronic transition, resulting into more absorption of light, hence more the amount of reflected light, and more will be the intensity of color. Right? Similarly, if the forbidden, then the things will be in opposite manner. Now, there are some relaxation in Laporte selection rule, but we will discuss this. We can say now we will discuss here also. If there are many complexes, uh, first we will discuss about spin selection rule. Then we will discuss about the relaxation in Laporte selection rule as well as relaxation in spin selection rule. Now the second is the spin selection rule, right? Spin selection rule. Spin selection rule suggests that the during electronic transition, there will be no change in spin state of the complex, spin state of the system, right? For example, during electronic transition, the difference between total spin resultant spin quantum number will be zero between two states. For example, if we have a state, for example, it is named as 3F, and we have energy level is now 3D, then electronic tension between two. This is the 2s plus 1 and 2s plus 1. This is the spin multiplicity. If spin multiplicity is same, then spin value will be also same because 2s plus 1, 3 here, this value is 2s plus 1, 3 is here. If both these values are same, it means s will be same. So difference between these two states, yeah, difference between spin quantum number or resultant spin quantum number between two states is zero. It means this electronic tension is spin allowed, right? Now, another example corresponding to spin selection rule. If we have a D5 high spin system and it is an octahedral environment, this octahedral system, and 1, 2, 3, 4, 5, and if this complex undergoes excitation of electron from this state to another state, that is light, and here is the absorption of electron from T2G to EG state like this, then the electron filling will be like this. Here the total value of S, this is the state 1. We can say energy level 1 as state 1. We can say state 1. And this is state 2. Why state 2? Because in state 1, all the electrons are unpaired. In state 2, there is one set of paired electron. So total value of S, right? S is the summation of S values. So 1 by 2, 1 by 2, 1 by 2, 1 by that is 5 by 2. Here, for example, is S1. Here S equal to S2 equal to 1 by 2, 1 by 2, 1 by 2, 3 by 2. The difference between these two states, state, this first state and this second state, the electronic transition in electronic transition occurs between S1 state and S2 state. Because on absorption of light, there is formation of this state. It means on absorption of light, electron is moving from this S1 state to S2 state. The difference between S2 minus S1 should be what? 0. But here is 3 by 2 minus 5 by 2, that is minus 1, right? It means the difference between the spin quantum number of difference between spin quantum number between these two states is not equal to 0. It means such kind of electronic transition is not obeying spin selection rule. It means the electronic transition in D5 high spin system, electronic transition in D5 high spin octahedral system is spin forbidden, not spin allowed, right? Similarly, you can predict uh, the validity of we can say the allowedness of spin selection rule in different kind of complexes. For example, if we have a complex like D4 high spin octahedral, for example, we have a D4 high spin octahedral system. Okay, here we have D4 high spin octahedral like this: one, two, three, four. On absorption of light, this will leads to formation of this particular state. So one, two, three, four. Because this energy level is vacant, therefore electron will lie in this energy level. Okay, yeah, this energy set. Here the S value is equal to 1 by 2, 1 by 2, 1 by 2, 1, but that is 4 by 2. Here the S value will be also equal to 4 by 2. This is the S1. The we can say the spin quantum number of the first state and the spin quantum number of the second state. These two states are involved in electronic transition. The difference between S2 minus S1 is equal to 4 by 2 minus 4 by 2, that is 0. So here the delta S equal to 0. It means the electronic transition in case of D4 high spin complexes is spin allowed, unlike electronic transition in D5 high spin system. This is the spin allowed. Okay, similarly, we can predict in most of the complexes that we can predict the allowedness of spin selection rule in all the complexes. We have idea of the spin state, whether the complex is high spin system or whether complex is low spin system, or we have the idea of the energy levels. That is the term symbol. We will discuss about term symbol later after discussing the DD transition, charge transfer, and other region that are responsible for color of coordination complexes. After that, when we will start discussing or we will start uh, studying about Orgel diagram or electronic spectra, then we will first discuss about the term symbol. What is term symbol? What are the microstates? Then we will discuss about Orgel diagram and number of electronic transition. How we will be able to predict the delta value, number of absorption band on the behalf of the Orgel diagram, or that we will we can say that outcome of the Orgel diagram. Now, these are the selection rules that must be followed by any complex in order to show a good, or we can say a better electronic transition and better absorption of light, right? So if any complex do not obey any of the selection rule, either Laporte selection rule or spin selection rule, then there will be either no possibility, we can say there will be zero possibility, or very some possibility of electronic transition that will leads to absorption of either no light by that particular complex, or absorption of very small light that will leads to either colorless system, or there will be some very weak color, right? Similarly, if any complex follow both the selection rule, then there will be more possibility of absorption of light, hence more intensity will be color. If any complex obey only one of the selection rule, either spin selection rule or Laporte selection rule, then tendency of electronic transition will be less. Hence, the tendency of absorption of light also will be less. It means they will leads to medium color. That is the color that is lesser as compared to the complexes. The those obeys both the selection rule and the complexes who do not obey any of the selection rule, right? Here, one thing we have to remember: there are complexes which do not obey either Laporte selection rule and also do not obey uh, complexes do not obey the spin selection rule, but they have very small color. We can say they show very weak color. Means they do not obey Laporte selection rule properly. They do not obey spin selection rule properly, but they show color. It means there is some electronic transition. It means there is some absorption of light that is responsible for color of that particular complex. Why this is so? Why it is like that? Any complex do not obey. For example, if we have MnH2O6 2 plus. This is D5 high spin system octahedral. This D5 octahedral system is like this: 1, 2, 3, 4, 5. Right? If we excite electron from this energy level to this energy level like this, then this the arrangement of electron will be like this. But there will be pairing of electron in EG set, right? Here the S1 value is 5 by 2 because there are 5 unpaired electrons. Here S2 value, that is the total spin quantum number, the second state will be 3 by 2. The energy, the difference between S values is 3 by 2 minus 5 by 2, that is minus 1. Means the electronic transition between these two state or electronic transition in this system, delta S is minus 1. That is, this kind of electronic transition is spin forbidden, not allowed. Means the D5 high spin octahedral system, yeah, we can say in case of D5 high spin octahedral system, the spin selection rule is forbidden. Now, if we talk about, if we look the possibility of allowedness of the Laporte selection rule, then is the d orbital having L value is equal to 2. Similarly, it is also d orbital having L value equal to 2. So, difference between delta L, the energy, yeah, we can say this is a state. Electronic tension occurs in this and this energy level. The L value for lower energy level is 2. L value for higher energy level is also 2. So delta L will be 0. It means this kind of transition, because it is example of DD transition, it is also Laporte forbidden. Means the electronic transition in case of MnH2O6 plus is both spin forbidden as well as Laporte forbidden. It means this complex, we can say that in this complex there is no possibility of electronic transition. Hence, this complex should not absorb any light. If the complex will not absorb any light, then it will not reflect any kind of light. It means it should be colorless. But it has been found that the complex has very weak color, yeah, very light color, very weak or very light color. That is pale pink. You don't have to remember the color because we will not we are not able to remember the color of the complexes because color of all the complexes depend upon the energy difference between lower and high energy level. That is the delta, right? We can predict where will be the high, in which complex the delta value will be high, in which complex the delta value will be low, but we will not be able to predict the exact value of delta. So you don't have to worry about the color. Here I have just uh, I have just told you about the color just for explaining that if any complex, the complex like MnH2O6 plus, it doesn't obey spin selection rule, also it doesn't obey Laporte selection rule, although it has very weak color. It means there must be some absorption of light. And absorption of light occurs only when there will be some electronic transition. Why there is electronic transition MnH2O6 plus, although it doesn't obey spin selection rule as well as Laporte selection rule? It is because of relaxation in spin selection rule as well as Laporte selection rule, right? The color of MnH2O6 plus or pale pink color of MnH2O6 plus is because of absorption of very small amount of light and very small amount of electronic transition. Why there is very small amount of light or very small amount of electronic tension? Because of relaxation that is going to happen, that is happening in spin selection rule, and relaxation that is happening in Laporte selection rule. Although strictly they do not follow spin selection rule as well as Laporte selection, because it means both this complex is showing spin forbidden condition or also Laporte forbidden condition. But very weak color or light color is possible only when there will be some absorption of light. Absorption of light suggests that there must be some kind of some very small amount of electronic transition. Why electronic transition? Electronic transition is possible only when there will be some relaxation in the selection rule. So the color of MnH2O62 plus, the very weak color or very light color of MnH2O62 plus is because of relaxation in spin selection rule or relaxation in Laporte selection rule. It means there are many complexes which do not obey Laporte selection rule, which also do not obey spin selection rule, but they show very small or very weak color, very light color. This is because of the relaxation in Laporte selection rule and spin selection means Laporte selection rule and spin selection rules are strictly valid only when only a particular condition, not in all condition. If complex do not follow, we can say complex do not follow that particular condition, then there will be relaxation in Laporte selection rule. Right? For example, there are many instances you have seen in your daily life that if you are belonging to a particular person that have some either politically well connected or we can say that administratively well connected, then your work related to government offices or your other works will be very easy. But for a common man, this is very difficult, right? Because rule for common man is strictly followed. The rule for the other person, this is the destiny. This is the reality of every nation is little bit easy. Similarly, here, spin selection rule and Laporte selection rule are valid only a particular condition. If any complex is showing different kind of uh, yeah, we can say if any complex has some different kind of uh, orientation or we can say different kind of behavior as that has been mentioned for Laporte selection rule, then there will be relaxation Laporte selection rule. And relaxation is leading to the very small amount of electronic transition, hence very small amount of absorption of light, hence very weak or light color. So the weak or light color in many or complexes which do not obey both the selection rules is because of relaxation in Laporte selection rule as well as spin selection rule. Okay, so we will discuss about the relaxation in selection rules, right? First, relaxation in Laporte selection rule. Okay. Now, listen. The Laporte selection rule is strictly valid when there is center of symmetry. What is the center of symmetry? If you move from the center in opposite direction, then there will be same kind of system or same kind of species at same distance. Then this is called this complex as center of symmetry. For example, octahedral complex has center of symmetry, but tetrahedral complex do not have center of symmetry, right? So first, in case of tetrahedral complexes, yeah, we can say that Laporte selection rule is relaxed. Laporte selection rule is relaxed when there is deviation from center of symmetry, right? When there is, for example, if molecule is perfectly centrosymmetric, then Laporte condition is that delta L should be plus minus 1, right? But when there is deviation from center of symmetry, then there is some possibility of mixing of orbital. Mixing of orbital leads to the possibility of relaxation of selection rule, right? In first example, we are going to discuss about this. The Laporte selection rule relax when there is deviation from center of symmetry. For example, tetrahedral complexes do not have center of symmetry. As they do not have center of symmetry, there is PD mixing in tetrahedral complexes. As they do not have center of symmetry, there is possibility of PD mixing. Means in case of tetrahedral complexes, that these two energy levels, this E energy level and this T2 energy levels, are not purely D energy level, right? These are E and T2. This T2 is D, but this E energy level is formed by the mixing of P and D. Means the E set has the character of both P and D set, while T2 set has the character of only D set. It means here the mixing of atomic orbital. Why mixing? Because of deviation from the center of symmetry. So there are many complexes. When there is deviation from center of symmetry, means complex are not centrosymmetric, then there is some kind of mixing between energy state. Means the L value for this state is 2. Since this state is formed by the mixing of P and D, the L value is not equal to 2, right? So the electronic transition between two states, the delta L will not be equal to 0, right? It means also it will not equal to plus 1 or minus 1, because if we have P and D character, the value will be between 1 and 2, right? Means the value will be greater than, we can say greater than 1, greater than 1 and less than 2. So the difference between difference between the delta L, yeah, we can say difference between the values of L will not be equal to 0. It can be either 0.5, 0.2, 0.4, something, right? It means the Laporte rule is partly allowed. The fully allowedness of Laporte rule is that delta L is, if delta L is equal to plus minus 1, then it is fully allowed. If delta L is not equal to 0, means it can be 0.1, 0.5, right? You can say 0.7, or you can say 0.2, then it is either plus or minus, then it is partly allowed. Means Laporte rule is relaxed. Okay. This relaxation leads to excitation of electron from this lower energy level to high energy level. It is responsible for color of complexes, because if there is possibility of excitation of electron from T2 set the low energy level to high energy level, then there will be possibility of absorption of light that will leads to color of that particular complex. So in any complex or in any system, when there is deviation from the center of symmetry, then there is possibility of mixing of atomic orbitals or mixing of orbital that leads to the lose in the pure nature of the d orbital. We can say that the nature of d orbital is not pure. You can say the purity of d orbital is diminished, or we can say that there is character of different kind of orbital in given energy levels. That is why the difference between L value is not equal to 0. It can be plus minus 0.1, 0.2, at different values between uh, 0 to 1, right? It is not equal to 1 and not less than 0. Means the value of, in such cases, the value of the, in such cases, the value of the delta L will be between 0 to, we can say 0 to 1, right? As I have written it like 2 point, 0.1, 0.5, 0.7, 0.2. So all these system, all these kind of situations leads to partly allowance of Lefferts selection rule, hence absorption of light by the complex that is responsible for the color. Okay. So any complex, when there is deviation, more the deviation from the center of symmetry, more will the possibility of mixing of orbital, and so more will be the allowedness of Lefferts selection rule. Okay. So more the deviation from center of symmetry, more will be the relaxation in Lefferts selection rule. Here we have discussed about an example of tetrahedral system. There are many octahedral system where there is loose in center of symmetry during the asymmetric kind of vibration, but mixing in case of octahedral complexes is less because octahedral complexes are generally centrosymmetric. The lose a loss of center of symmetry occurs when there is asymmetric kind of vibration, and that kind of vibration occurs from very short time. So in that particular short time, there is mixing of orbital, and since that particular asymmetric vibration or situation of asymmetric vibration occurs for very few moments, so in that particular moment, there is mixing of orbital. That very small amount of mixing of orbital leads to very small amount of electronic transition, leading to very small allowedness of Lefferts selection rule. But this will be less as compared to tetrahedral because in tetrahedral complexes there is no center of symmetry at all. But in octahedral complexes, the lose in center of symmetry occur for a particular moment means very short time there is lose in loss of center of symmetry. Hence, for that particular moment, there will be mixing of atomic orbital, a mixing of orbital, and that leads to allowedness of Lefferts selection rule because but the relaxation Lefferts selection rule is very, very small as compared to the relaxation of Lefferts selection rule in case of tetrahedral complexes because are tetrahedral complexes do not have center of symmetry, but in octahedral complexes there is center of symmetry. The condition, the time when there is lose in center of symmetry or loss of center of symmetry is responsible for the very weak color of octahedral complexes. So here we can discuss about the here in octahedral complexes during asymmetric vibration, or we can say asymmetric stretching, right? There will be no center of symmetry, hence mixing of energy levels leading to very partly or very less allowedness of Laporte selection rule. Okay. So, for example, in case of MnH2O6 plus in this complex, why B color is the B color of this complex is because of relaxation in Laporte selection rule. When there is relaxation, when the MnH2O6 plus undergo asymmetric kind of stretching, then at that particular moment there will be mixing of energy levels. In that particular time, there will be excitation of electron. That excitation of electron will uh, occurs because of absorption of light, and absorption, if there is absorption of light, then there will be some possibility of color. As the time for this kind of stretching is very, very small, or this situation occurs for a particular moment, so mixing of energy level will be also very less, excitation of electron will be also very less, or similarly the absorption of light also will be very less, leading to the very weak color of such complexes. What is asymmetric kind of vibration? If we have a perfect octahedral complex like this, it has center of symmetry because from center, if we move from here, there is L. From center, if we move from the center, there is same distance L. Asymmetric vibration will be like this L, this L. There is no center of symmetry. Why? Because when we move from center to z direction, a positive z direction, then we have to travel more distance. While when we move from center to the z minus direction, for example, then we have to travel less distance. So there are ligand at different distance, right? While the meaning of center symmetry that if you move from the center to two opposite direction, then at the same distance there should be same kind of species. But in this kind of situation, you can say this is asymmetric kind of stretching, asymmetric kind of stretching. There are same kind of ligand which are present in opposite direction but at different distances. So in this situation, there is no center of symmetry. And because of this, there is some mixing of atomic orbitals or mixing of energy levels. There is the centrosymmetric system. So all the octahedral complexes when where there is no allowedness of spin selection rule or Laporte selection rule, if they are showing color, then the color will be because of this Laporte selection rule, and the relaxation of Laporte selection rule of such kind is because of the asymmetric kind of vibration. Okay, so this is all about today class. We will meet tomorrow at 8 a.m. and discuss the remaining part of the spin selection rule, that is relaxation in spin selection rule. Then we will come to the DD transition, chart transfer, and these other factors of the color and electron spectra topic. Okay, so take care. We will meet tomorrow at 8 a.m.